All right, everyone, welcome to the fifth and final problem in this set of review for dynamics for our biomechanics course. Full disclosure, I did just record a solution to this, and then when I got to the end, I realized that I forgot to account for the weight of this segment. So, got to be careful when working on these problems. I'm just going to go through and do the whole thing because I don't want to have to edit my solution. But make sure you're working as carefully as you can when you're working on these. All right, so this problem says an amputee falls and tries to catch themselves with their prosthetic arm. Force plates and motion capture were used to record the reaction forces and kinematics as shown. If the forearm and hand components have a mass of 4 kilograms and a rotational inertia of 2 kilogram meter squared, what are the reactions at the elbow as applied to the forearm using the directions as shown? All right, so in this problem, we're really just going to use our basics. Summation of forces, sorry, the wrong unit. Summation of force equals mass times acceleration. And summation of moments, we're going to use the center of gravity, is equal to our mass moment of inertia times our alpha, or angular acceleration. All right. First thing we want to do here is we probably want to establish a coordinate system to work in. So just to work on this problem, I'm going to use a positive y up and a positive x to the right, just because I'm more consistent or comfortable working in a consistent frame like that. You can choose any frame you want, but I really suggest that you try, or if you have the option to arbitrarily define a frame, to try and define it in the same way all the time, so that way you are less likely to make mistakes when you're working on things. I don't want to do the moments first, I want to do the forces first. It's typically a lot easier to solve for forces than it is for moments. And you'll have fewer unknowns when you go to write your moment equations, preventing you from having to then go back and resubstitute things in later. In this case, I'm not given a reaction for the x direction here with the contact, and I'm also not given a acceleration in the x direction in the problem. And whenever I'm not given something, assuming that it's not obviously an error in how the problem is written, I'm going to assume that that value is 0. So I'm assuming that I'm not giving an acceleration in the x direction because there isn't one. And I'm assuming I'm not giving a horizontal reaction force because there isn't one. So that makes our problem a little bit more straightforward. So let's take a look at summation of forces in the x equals to our mass times acceleration in the x. In the x direction, really all we have is our ex. So that seems pretty straightforward. I'm going to set that equal to our mass, and then our ax, which again, as we said, is 0. So this is going to be all equal to 0. Therefore, our ex is equal to 0. Super easy, fast and done. Y a little bit more complicated. One of the things here, I do know that this part does have weight, right? So it has a mass of 4 kilograms. So it is going to have a weight. And even if you're not given a weight of a segment or given a gravity, you should assume Earth gravity, right? So there's going to be a weight here of 4 times 9.81. So 4 kilograms times 9.81 meters per second. So I'm going to add that to my force equation. I'm going to do a quick calculation to figure out what that's at. That looks at 39.2 newtons. So in my summation of forces in the y, I'm going to have, I'm going to do upwards positive, 100 newtons minus my 4 times 9.81, which gives me 39.2, minus my EY. There's all my forces in the y direction. Again, making sure I'm including that weight portion. So that equal to my mass times acceleration. So we have 4 times acceleration in the y, 20. And note, this is kilograms, and this is in meters per second squared, and that's equal to newtons, right? And then these are both in newtons. So these are all basically going to be in newtons. It's important to keep track of units. If you're using something besides meters or something besides kilograms, or not very likely, but something besides seconds, you need to account for that when you wrote your equations. So we can solve this out. Our EY equal to, I'm just going to move everything to one side of the equation. We have 100 minus 39.2 minus 4 times 20, so that's 80. So I'm going to plug this in my calculator. And I'm going to get negative 19.2 newtons, right? Again, as was drawn, is drawn downwards, so I could also say 19.2 newtons upwards on the form. Doesn't make a whole lot of sense if this person is falling, but maybe they're trying to pull their arm back up after they fell because they're worried about injuring that residual limb or something to that effect, right? All right, so we got that. We can move on to our moments now. So if we do summation of moments, I'm going to switch to a different color just to keep this a little bit easier to see. Summation of moments about the gravity, center of gravity, equal to our IG alpha. So our first force here, we have 100. I'm gonna do clockwise positive. 100 newtons times, and in this case I have 2.5 minus 0.1. So this is distance is 0.15, 0.15 meters. My weight is going through the center of gravity, so I can ignore that. And then I'm going to clockwise, so this EY is still going to rotate kind of clockwise about that center of gravity. So my EY, but it was negative, so I'm going to leave that negative in there. 19.2 newtons times 0.1 meters. And our EX was 0, so we can leave that out. And then I'm going to add my ME. My ME is actually shown as being counterclockwise, so I'm going to do that as negative ME equal to our IG, which we have 2, times our alpha, which we have as 6. And important to note here, we have kilograms times, kilograms meters squared times our alpha, which is going to be 1 over second squared. So this is the same as kilogram meters second squared times meters, which is the same as Newton meters. So again, just checking to make sure our units are consistent across there. And again, if you're using newtons, kilograms, meters, and seconds all the time, that makes things a lot easier. If you're using something else, I would probably suggest that you convert to kilograms, meters, newtons at the start, and then go all the way through. All right, now we just need to plug and chug, right? So we have our ME equal to 100 times 0.15, that'll give us 15. We have 0.1 times negative 19.2, so that'll be negative 1.92. We have our 2 times 6, so that'll be 12. So I'm saying minus 12. And we just established that that is Newton meters. And so we can add all those up, or really subtract the 2 points from our 15. And that should give us 1.08 Newton meters. Again, we did this as clockwise positive, but we put in our ME as we wrote it. So we want to make sure we go back to our diagram for the actual directions here. So see our ME is equal to 1.08 Newton meters counterclockwise on the forearm, right? There's our answer there. And it's pretty common for us to see these problems where, when we take the summation of moments about the center of mass, for the forces on either side to kind of largely cancel out the net moment that's being applied to the problem. So the fact that we got a fairly small moment, even though the kind of the distal and proximal forces produced large kind of counter rotating moments. So, all right. Hopefully that was clear for everyone. If you have any questions, please feel free to let me know.